All right, so today we're talking about Newton's law of gravitation. This is universal gravitation, the gravity that applies everywhere in the universe. And here's how it works. You know from last year, it's actually GMM over d squared is the force, not r. And the reason that's important is, say you have two planets, a little one on the outside and a big one in the middle. And actually, which one has to be more massive in this picture? Do you know?
The outer one.
The outer one or the inner one is more massive? Uh-oh.
The inner one has a smaller radius.
No, because if it was the bigger one was the inside one.
Think about this. Don't you know that objects will rotate about their center of mass?
Yeah.
Where's the center of mass? Is it closer to 1 or 2? Closer to 1. So which one has to be more massive? 1. Got it? The way the picture's drawn is a little misleading. All right? In fact, if it's a 1/3, 2/3 relationship, then we know that mass 1 has to be double that mass 2. Does that make sense? And if they're equal, then they're both orbiting with an equal radius, because equal mass, equal center of mass, all that. So the easiest way to look at these problems where you've got something orbiting something else in a circular orbit is just look at the location of the center of mass, and from that you can backtrack and figure out what the relative masses are. All right, so if one has a radius of r and one has a radius of 2r, then that means the inner one is twice as massive as the outer one. Okay, moving on. But the key thing here is for the force of gravity between them, you don't use r, you use d. Good? You also know from last year that, what's big G?
6.0.
Yeah, but what is it conceptually? It's a gravitational, it's just a number. It's just a number that shows how strong gravity is in the universe. All right? It's a constant to make all the rest of the numbers work out. And there's a couple of these in physics, about 6 of them I can think of. Do you guys know any other universal constants? Is 9.8 a universal constant? No, that's only for Earth, right? Planck's constant.
Atomic number.
Boltzmann constant.
Or Avogadro's number.
Avogadro's number is not a universal constant. That's not a universal constant. It's just a number. It doesn't relate to things, really. I suppose it relates grams to atoms, but that's a completely arbitrary thing. I was going to say another one would be either Coulomb's law or the permittivity of a vacuum, depending on which one you want to go with. And then there's one for magnetic permeability as well that we're going to talk about later. So anyway, yeah, the universe has several of these constants that we're going to run into in this class. All right, so most important thing in gravity problems, anytime you got stuff orbiting, use d, not r. Got it? Okay. Now, so have we had a discussion, I can't remember, have we had a discussion about the difference between a law and a theory? Did we mention that at all? Which is better, a scientific law or a scientific theory?
Law.
Who says law? Because that sounds legal, right? Who says theory? Interesting. Like 3 people in the room say theory is better than law, and like most of the room says, oh no, law's better. What's the difference between a law and a theory? A theory isn't accepted. Is that what you said?
No, it's accepted, but it's not fully given.
Interesting.
It hasn't been tested enough.
Very interesting. So we think that the law is like the ultimate goal of science is to come up with laws, right? Wait. Suvi, you say the ultimate goal of science is to come up with theories. Very interesting. Why do you say that?
Can we choose answer C?
Laws are just observations of what happened.
Yes! Say that again louder.
Laws are just observations of what happened.
Okay, ready? I'm going to make up a law right now. You ready? Here we go. This is Mr. Bruce's law of falling keys. They fell! Let's try it again. Oh my God, they fell again. They fell again. What if I throw them up? They fell again! Holy cow! So, Mr. Bruce's law, scientific law of falling keys. When I do stuff to the keys and I let go of them, they fall. Congratulations, go me. I just made a new scientific law. The law of falling keys. Got it? How hard is it to make a law? I just did. Good job. How hard is it to make a theory? A scientific theory.
Very difficult.
If you ever make a scientifically accepted theory, you might just win a Nobel Prize. Got it? What's the difference between a law and a theory? Suvi perfectly summed it up. That was exactly the right answer. A law is something that you can just, it's just a statement of observable fact that tends to repeat itself. All right, for example, Newton's second law of motion. What is it?
Conservation.
Yeah, the acceleration of an object depends on the force. Is it true?
Yeah.
Is it true? Does it always hold true? Nope. Nope, it doesn't.
All for light.
Right? Because Newton's second law of motion says if you keep on going, if you keep on applying a net force, you'll keep on accelerating forever and ever and ever and faster and faster and faster. Can you? No, you're limited by the speed of light. Newton's second law isn't even true. And yet we say, oh, that's okay. We can use it. It's just as long as we're not going speed of light and or we're not talking about stuff on the quantum mechanical scale. Just as long as we're not going real fast and we're not talking about real small stuff, we can use Newton's second law. Got it? I am going to save that for a different course. I don't want to go there quite yet. Mr. Torp talks about, he's actually talking about that right now in advanced physics. All right, but yeah, in classical mechanics, they didn't know that the speed of light was a limit. But Newton certainly didn't know that. He didn't even know what atoms were. Or if he did have a concept of atoms, it certainly wasn't the same concept of atoms that we have today. So, a law is simply a statement of observable fact. Anyone can come up with a law. But what does it take to come up with a theory?
Lots and lots of testing.
Lots and lots and lots of independent verification. Okay, here's one of my favorites. You're talking, you're over break, family's home, whatever, everybody's talking, and somebody brings up evolution by natural selection. You say, well, evolution's just a theory. And what do you say? Thank you. Why? Because theory is the pinnacle of scientific achievement. See, it drives me, all these crime shows like CSI drive me absolutely crazy because they're like, oh yeah, okay, our theory is this about what happened in this case, right? And then they come up with a theory on a whim and they're like, well, yeah, but that's just a theory. I have a theory that goes like this. Is that the way theories work in science?
No.
No! What do we call that? Something that's untested. That's called a hypothesis. I can come up with a hypothesis. I can come up with a hypothesis of why stuff falls. I think it falls because keys are naturally attracted to dirt. Right? Because they came from the dirt. Right? That's my hypothesis. And then I can test that. And I discover, well, you know, that's maybe not such a good hypothesis after all, but I'd have to test it to verify that. Is a theory untested? No. What is a theory?
It's
Some thousands of people have conducted millions of independent experiments all over the world. And eventually, we come up with a theory that stands the test of time. And what is a theory? It's better than a law. A theory is an explanation of why things happen. A law is simply a statement that this appears to happen. All right, so what's the difference between Newton's law of gravity and Newton's theory of gravity? What's Newton's law of gravity? Oh my gosh. That's like Mr. Bruce's law of keys, of falling keys. No. What's Newton's law of gravity? GMM over d squared. Right. That's his law of gravity. What's his theory of gravity?
The force of attraction depends on the mass of the two objects and the distance between them.
All right. Here is the complete version, or the three main ideas of Newton's theory of gravity. First big idea in his theory of gravity is the law of gravity. The force of attraction between two objects depends on the mass of the two objects and how far they are apart. What's that? That's the first piece of the theory. The law is the first piece of the theory. The second is called the Principle of Equivalence. And it says something like this. Did I tell you the story about the trick-or-treaters and the two kids and the younger brother and the older brother? I never told that story? Oh my gosh, how did I not tell that story? Okay, so a few years ago, for Halloween, I decided that I was going to draw a big maze on my driveway, and the kids would have to come through the maze, and like if they went the wrong way, they'd run into a ghost or a skeleton or something. So big maze all over my driveway that kids could go through. Then once they came to the maze, they came up to the door, and then of course they come to the door and they trick or treat. But I felt bad about giving so much candy because too much candy's bad. So I gave them like mazes and pencils and stuff. There's the younger brother and this older brother. One of the older brother's like 9 and the younger brother's like 6 or 7. They come up to the door and they dressed up and I said, okay, and they go trick or treat. And I say, okay, good, trick. And that's what it means, right? It's trick or treat, not automatically treat. So I said, okay, so you can have candy if you can answer the following question.
Oh, I got it. That's cute. Needless to say, at the end of the story, Mr. Bruce's house got egg.
So I said, okay, I have a basketball and I have a tennis ball here in my hand. If I were to hold them both at the same height and let go, which hits the ground first?
I didn't even know that question.
And of course, that's a hard question, right? Which is going to hit the ground first? What do you guys think?
Basketball.
Basketball, right? So the older brother looks at the basketball, he looks at the tennis ball, picks up the basketball, holds it like this in his hand, and picks up the tennis ball, holds it in one hand, and he looks at it and he says, "Whoa, yeah, the basketball. The basketball is going to hit the ground first. Why? Because it's heavier. It's getting pulled harder, right? It's going to hit the ground first." And then the younger brother kind of scratches his head a little bit and looks at the two balls and can I pick up the balls? And she says, sure, you can pick up the ball. So he picks up the basketball, in both hands and feels it a little bit, and then he starts like trying to shake it back and forth. Puts the basketball down, and he picks up the tennis ball and back and forth, real quickly, real fast. Puts that on there. Says, I think the tennis ball is going to hit the ground first. How come? Because it's easier to move. Right? It should hit the ground first. It's easier to move. So who's right?
Neither.
Both.
They're both right.
And that's why they'll hit the ground at the same time.
Yep. Both effects cancel. What are the two effects? Well, one of them, the older brother, was talking about the force of gravity. And the younger brother was actually talking about something called inertia.
And a 6 to 9-year-old can do this?
Absolutely. So I gave him both candy. So like all stories in this class, there is at least some kernel of truth. I did do a maze, and yeah, anyway. I did one year give out maze little pencils and stuff. This was a few years ago. Yeah, so anyway, but the point is, this is actually called the Principle of Equivalence. And Newton came up with this idea, is that mass has two effects. One of the effects of having mass is that there is gravity. Things with mass attract each other. The other effect of having mass is there is inertia. And these two things always happen whenever you have more mass. You have both more gravity force and more inertia. The two effects of mass. And that's the second. That's called the Principle of Equivalence. It's the second part of his theory of gravity. Third part of theory of gravity, this is the big one. The three laws of motion are applicable everywhere in the universe. Meaning, and this one is huge heresy. If you think about what the religious teachings were at the time, what did they say? There's the heavens, and then there's earth, right? And what did Newton say?
Heresy is no difference.
There's no difference. Could you imagine how that must have gone over? When the church is talking about angels and archangels, and here Newton is talking about, well, the stuff up there is obeying the same rules as the stuff here. Holy cow. Could you imagine how that went over? Fortunately for Newton, there was a guy by the name of Galileo who came before him. And what happened to Galileo? Oh my gosh, did he have issues. Right? Well, the other part of... Do you guys know where Galileo lived? In a town, yes, in a town. He lived in a town. Yes, he lived in Italy. He lived in Italy. Where did Newton live?
Didn't he live right in the
Was he in Britain?
Oh, Germany.
Newton?
No, wait.
Isaac Newton? What kind of a name does that sound like?
Newtown. He lived in Newtown.
Yeah, he lived in Newtown, Connecticut. No. Where's Newton from? What's his name?
Isaac.
He's English. He spoke English. Where did he live? England. Wait a second. What's the difference between living in Italy and England? 300 years ago.
Catholic and
Next to
Protestant. England was Protestant.
Galileo was right next to the Roman Catholic Church. And Newton wasn't. Newton was in Protestant England. Got it? So Galileo was subject to all sorts of pressure, right? Whereas Newton was a little bit freer to speak whatever he thought was the truth. All right? Plus it also helped that Galileo, I think he died the year that Newton was born, is that right? I don't remember. Anyway, Newton was a real jerk. He was you could read up on him. He rarely gave people credit for anything. He liked to take credit for things, but one of his most famous quotes is, "If I have seen farther than anyone else, it's only because I've stood on the shoulders of others." All right? And who he was specifically referring to is Galileo. Newton's first two laws of motion are actually Galileo's first two laws of motion. Yeah, the law of inertia is Galileo, and the acceleration of an object is also Galileo. The only one that's actually Newton's alone is the third law, which is the action-reaction law. All right. So anyway, kind of a little tidbit of history, but anyway.
He used to stick things in his eyes
Oh yeah, he did all sorts of crazy stuff.
He used to figure out optics things. He used to stick things in his eyes. I don't know what he was doing.
Oh, he was crazy. He was an alchemist, and they suspect that because of the mercury he was exposed to, he went loop-de-loop.
Did he ever create gold?
What's that?
Did he ever create gold?
Did you ever create gold? Yes, from gold.
Yes.
He's probably one of those crazy chemists who used to pour the chemicals in their mouth and swish them in their mouth and then pull them back.
Yo, absolutely. He was poke stuff in his eye and he's weird, a weird dude. Anyway, Newton's theory of gravity, the first part of the theory is the law, and then the second and third parts are explanations of things that must be true in order to have a complete theory. But maybe the most important part was the third one, which said that the law of gravity, this happens for the same reason that Earth goes around the sun. And now it seems like no big deal, but at the time, that was a huge deal to say. All right? Heavenly things operate by the same rules as earthly things. Good? All right. So let's move on. So that's a little history lesson. Let's move on to some math. Gravitational potential energy. You guys remember how to figure out the potential energy of something? How do you do it?
Mass times gravity.
Well, assuming it's a conservative force, you use work, right?
Yeah.
Work. Work. W-O-R-K, work. Because if you think about it this way. If I take a 1 kilogram mass and lift it up 1 meter, how much work did gravity do? Negative 9.8 joules, right? And the way we did that is we said, well, the work done by gravity is negative, but assuming it's a conservative force, then the negative work equals the gain in potential energy. Does that make sense? So we're going to apply that same logic, but this time we're going to do it over a big scale where g is not constant. So here's how it's going to work. First of all, we're going to say that if you have the sun, if you have Earth at position 0, what happens to your energy as you get closer to Earth? You lose potential energy, right? So here it has more potential energy, here it has less potential energy, right? How much potential energy does it have when you're infinitely far away from Earth? Wrong. 0. Why? The force of gravity gets weaker and weaker as you get further away, right? So yeah, you're gaining energy as you get further away, but the further away you get, the less and less energy you gain per meter, right? Right? So you get to a certain point, you're not really gaining any energy, or gaining very, very, very little once you're like a couple light years away, right? So what do you call that energy level? Do you want to call it infinity? Well, that would be weird. Call it 0. Yeah, that makes more sense. Because if you're going to call it some number that's not infinity, what's the next logical choice? 0. Which means, oh, this is interesting. As you get closer and closer in towards Earth, you come this way, you're losing energy, right? But if you started at 0 and you come this way, closer towards Earth, what's your energy becoming?
Bigger.
More and more negative. So a rock will fall down this hill, right? Gee, isn't that interesting? Now, radius of Earth. At the radius of Earth, if we just go from here to here, how much is the gravitational force on this object changing? Almost imperceptibly small. So from this range, from here to here, we say that that force is pretty close to constant. Even though the slope would change ever so slightly, you're not even going to notice it. And so near the surface of Earth, we say that the slope of the gravitational potential energy line is pretty constant. Does that make sense? It's something called the flat Earth approximation, which basically says if you have an infinitely large object, what's going to happen to gravity as you get further and further away? Actually, no, it's not. Think about it this way. Let's say these pencils are on this table represent gravitational force, or the gravitational field. Which way are they always pointing? Down, towards the table. Would you agree that if this table were infinitely large... Oh, sorry. What do you notice about these two lines? They're parallel. So, if you get up here, are they still parallel? Yeah, they still are. Now, just as long as this table is infinitely large, we could say these lines are forever parallel, right? So does the field ever get weaker? No, because they never spread apart. So if you had an infinite planet, gravity would never get weaker. All right? Now, from our point of view, and the planet would have to be totally flat-shaped, right?
It's okay, that's how it is.
Yes, the Earth is flat. It's called the flat Earth approximation. The flat Earth approximation, the way the physics works out, is that if the Earth is flat and goes on forever, gravity would never get weaker. All right? Does that make sense? All right. Okay, moving on. This approximation is valid for us near the surface of Earth because the planet is so huge compared to us that we're never going to see the effect of weakening gravity. But if you go out on a trip to the moon or something, then you will definitely feel the effects of weakening gravity. Does that make sense? All right, cool. Okay. Here is the real expression. You know gravitational potential energy is mgh, right? Wrong. The real expression for gravitational potential energy, you'd have to do the integral of the work, right? The work integral. But what would you use as a force for that integral?
You use
GMM over d squared. So we have to integrate that with respect to d. All right? So here's what the integral looks like. The change in potential energy when you go from one position to farther away would be the negative GMM over d. Actually, I called it x because dd would be weird. GMM over x squared, right? dx. What's that integral? GMM over x squared dx. How do you do that? Power rule.
It'd be 1 over...
It'd be a negative.
Negative.
Because it's over x squared, right? And then what do you do with the power?
Decrease.
Yeah, so instead of x squared, it'd just be over x, right? So the gravitational potential energy would be GMM over x, right? And then I've got a little thing, if you're going from r to infinity, well, the energy at infinity is 0, so the change in potential energy to go from r to infinity would be GMM over r. So hold on, let me explain this negative sign for a second. If you went from here to infinity, that means you gained GMM over r worth of energy, right? So if you went from infinity to r, what would happen? It'd be negative GMM over r. Good. So gravitational potential energy is negative GMM over r between two objects. If you want to figure out how much energy is stored in the gravitational field between two planets that are apart by some distance, you take the mass of one planet, mass of the other planet, divide by the distance between them. Make sense? All right, that should be GMM over D, sorry. Negative GMM over D. And here's the kicker. It's a negative value. It's a negative. Energy is negative. Gravitational potential energy is always negative. And then the reason it has to be negative is because it's always attractive, and you're always losing energy by getting closer. Sound good? All right, that's it.